our second tutorial of question 3 is that with EEG signal, here that we would like to know that we have actually 8 simultaneous channels are recorded and they are recorded at 100 hertz. We would like to find out whether the alpha rhythms are present, and for that a part of the signal would be taken which has clear actually presence of alpha rhythm. With that as a reference or template, we would like to find out that whether alpha rhythm is present in all these signal, and for that we will use the cross correlation of the template. Okay. So, this is the task, and so let us proceed for that. So, first thing is to collect the data file and that the MATLAB file to read the signal, and then we need to keep them both the input signal and the MATLAB code in the working directory of the MATLAB in the same directory. Next, we would like to see that signal. So, first we are using the load command to get EEG1 -F3 to load this data file, and we store that in the variable EEG F3. So, next we need to see the plot, and for that first we initialize the variable Fs, that the sampling frequency 100 hertz, and t is the time. It is 1 to that the length of the signal is giving the ramp divided by Fs, or we can say multiplication with 1 by Fs is giving us the time instant of each sample. Okay. So, that the sampling interval, if we multiply, we get the in second, we will get the value in the variable t. So, we plot the EEG signal with respect to the time. So, here is the signal. Here some part we can see that it looks like EEG is present, these parts. Okay. So, clear that alpha rhythms are there. So, next we have to find out a template, and for that we are taking that the P3 channel. So, we again follow the same procedure as the previous one, as we have taken for the previous channel, and we plot that signal. Here we get that channel, and with the help of an expert we select this part. Please keep in mind, the selection of template is very crucial operation, and someone who knows that waveform should select that. Okay. So, the success of the technique completely depends on that template. So, once this selection is done, that manually this part, it is in between starting from say 4 to 5 seconds and ending in between 5 to 6 seconds. This segment is selected. So, we would like to see that we check and find that this signal is template is actually in between 470 to 570, 101 samples are there in the EEG P3 signal. So, that we are taking as template. Okay. So, variable length of the template is taken. So, here instead of assigning any variable, we are taking the time instant corresponding to that starting from 470 to 570 samples. With respect to that, this is plotted. Here is the template. We get the template here starting from 4.7 to 5.7 second. Okay. So, this is our starting point for the template matching. Next is we have to take the correlation. So, for that here we start that operation. We have taken EG_F3 is the signal. Okay. Now, when we take the correlation, we are taking between EG_F3, say here is the signal and here is another small signal, that is template. Now, the overall length would be actually that we need to add, if this length is A, this length is B, overall length would be A plus B minus 1. Okay. But we do not want to see it in that way, rather we would like to have same number of points as A. So, how do we do? We take the midpoint of the template, assign it here and then slide it till this end. And in that way what happens? We have some samples here outside, here some samples outside. So, to take care of them, so that it does not become computationally infeasible and give error, we have to pad actually our signal both the side, and padding would be that we have 101 samples, that is the length of the template. So, if we divide by 2 and take the floor, we get 50. Okay. So, we take 50 zeros at the beginning, 50 zeros at the end, and that is the way that we have added. And here F3 was a row vector. So, to make it a column vector, so we have taken that 0, 1. So, please look at that it has become a column vector, and for that we have used that the transpose operation. So, that is a minor thing, but these things are very important to write the code properly. Next, we go through the main part of it. We take the product of the template and the part of that signal, that I would say that padded EEG signal, that is kept at x1, and we are taking that sample by sample product, okay, or dot product. For that the symbol is dot star. Okay. So, we are taking that product and then we are taking the sum of that. Okay. So, we can say this is doing the multiplier accumulator operation, MAC operation in short. And we are not just satisfied to take auto correlation or cross correlation, we have to take cross correlation coefficient. In other words, we need to normalize it with the strength of the template as well as strength of the signal. Otherwise, any variation in one of them will change that value of that correlation function. So, what we do? We divide it by that the norm of x1 and norm of the template. Now, what it does? Say if we have a vector x with all these values x1, x2, xn, okay. Say this is a vector, maybe it is a column vector. Now, when we take norm, it will calculate x1 square plus x2 square. So, in that way xn square, all of them it will add and it will take square root. That is the output of the norm function. Okay. So, we divide it by the norm of the two constituents, one is the template, another is the that part of the corresponding part of the signal. Okay. And here please look carefully that what we are trying to do, that we are sliding the window. If this is my padded signal, I am starting from here, or rather let us draw it in this way, that up to this, if this is the center, this part is the padding, zeros are there. Same way at the end some paddings are there. So, we will actually slide it from here to here. Okay. So, that is the way it is going. We are starting that j to j plus length of the template minus 1. Okay. So, from here to here. So, that is the way we have taken this part. And once the correlation is computed, then we have to plot that thing. So, we issue the command figure, then divide the pen into two parts. The upper part is subplot 2 1 1, then there we are plotting the signal. Okay. With, and here instead of the time we are giving the sample number, and we know our correlation function, that cross correlation coefficient, it also has same number of samples. So, we are using that index here to plot that thing. Okay. So, these two things are plotted one after another. So, here at the top we see the EEG signal F3 and below is the cross correlation coefficient. And what we see, that at some parts that high oscillations are there, that means some peaks are there with high value, that signifies that there is a match. Okay. Otherwise, it would be very flat kind of structure if it does not match. So, this oscillation itself talks about that there is a match, and immediate question could be that why there is an oscillation if there is a match. The reason is, say let us take two sinusoids to understand that. So, let us take one sinusoid is there and we have taken a small template of the same sinusoid, okay, a small part. A small part of it we have taken as template, and here if we slide it, if we take the template in this direction, when it is aligned it will give high value, when it is placed here it will give negative value, but high value, in between it will give no match, 0. So, that is the reason for oscillation. Again here it will give a high value. So, that creates this oscillation. Okay. So, that periodic nature of the signal gives rise to this oscillatory kind of output in the cross correlation coefficient. Next, to get a objective value whether this is high enough, we need to do the thresholding. So, for that what we have taken? We have taken the that maximum value of the cross correlation coefficient, half of that. If you are very restrictive, you can directly go for that 0.5. Okay. So, after taking the threshold, we collect the bin information when the cross correlation coefficient is above the threshold. So, this operation will give us that indices where the value crosses the threshold. Now, if we multiply that bin location having value 1, if we take the dot product with the cross correlation, we retain only those high values and rest of them become 0. Okay. So, let us proceed. Now, we would like to see that how it looks like. We again use the subplot command. The top portion we have taken 2 1 1 and plotting the cross correlation first. Next, that we are taking plot 2 1 2, that means the lower half, and we plot the thresholded the cross correlation, that is given as cross TH, okay, thresholded cross correlation coefficient. So, in the right hand side we get that, and we see here only one peak was prominent in this part, here 2 peaks were prominent, here multiple of them were there, here also multiples are there above the threshold. Okay. And as we have thresholded, we are getting that only the high values. When it is below, we have actually discarded the lower part. Okay. And there is one more reason, we will come to that the lower part also could have been useful for the purpose of detection if only one or less than one cycle was there, but in this case we have multiple of them. So, it should not have any problem. So, next what we do, we create the histogram of delay between the peaks. Now, why we are interested in the delay of it? The delay between the two peaks will give the length of that oscillation or one cycle of it. Okay. So, we would like to find that, because that will give the periodicity of the signal. So, for that what we do? We start with the correlation threshold, and we need to identify the correct location of the peak. So, for that we go through that thresholded correlation, and we are measuring that where at location j, if it is higher than the previous sample and it is higher than the next sample, then we can tell that a peak has come, and we store that peak location. Okay. And we increment the count and that how many peaks have found. So, we proceed in that way. Then once we take the difference of this peak location, we get the peak location delay. Okay. So, now we have the peak location delay. Next, with the help of that we find out the histogram, that we create the histogram of peak location delay, and as there would be number of them, okay, number of values would be there, we are restricting it into the first 50 delays, okay, because high values with very least count, they are not of any use. So, we restrict it there, so that we get a good picture, and we plot that figure, and here we are actually keeping only the counts. The second variable we are using tilde just to tell that we do not need to store that variable. Histogram is giving two outputs, the next one is not required for our operation. And we use the command stem to plot that, that means it will give us post kind of structures. Okay. So, let us see that how it looks. Okay. Before that before we go for the plot, we check for few more things, that for our operation after the histogram, that we would like to see that where the count is maximum, in which bin the maximum counts are there, that is the we are getting the mode of the delay, and we find out the location of that gives us that this much delay is occurring most of the time, and this delay however in terms of number of samples. So, to get the frequency, we need to normalize with the sampling frequency. So, we need to take care of that, and the corresponding frequency of oscillation is given here. Okay. So, let us proceed, that here is the plot, the stem plot, and what we get, that this is the highest count. So, we have taken the position here, it would be 11, we have taken that, and now that is converted to frequency and appropriately normalized with the sampling frequency, and in that way we expect to get the result. So, for each of these signal that we get that each of these case that it is giving us a little more than 9 hertz actually frequency, and we know that we have a range for the alpha, it is within that range. So, first we go through the output of the F3, we get here is the signal is not very clean, but time to time alpha are there. So, that is depicted by the correlation, that high value of the correlation coefficient is suggesting that. Okay. And once we threshold it, we get that minor occurrences also, and when they are having the very close actually occurrences, that helps us to get the delays. So, with respect to that, we are getting the maximum value here, and corresponding to that we have calculated the frequency. Okay. Next, we go for the next signal F4. The same way we have calculated the autocorrelation coefficient, thresholded it, and find out the peak of the histogram and the corresponding location for F4. So, next we go for F5, again we find the peak at the same location. Okay. This is EG C3. Next we go for C4, same nature. Next O1, again we have the same nature, O2, P3, P4, all the cases we got very similar output, and hence we summarize that our finding. Our observations are, we have the template of alpha rhythm that is cropped, and we take the cross correlation of each signal for the purpose of the analysis. Here please keep in mind that selection of the template is very crucial. Only an expert can pick that. Without that, a proper selection of the template, the whole technique will fall apart. Next, what we get, that alpha rhythm, we know the range of it is within 8 to 13 hertz, and our histogram peak we get at 9 hertz, which falls very well within this range. So, we can say for each of these 8 signals we had alpha rhythm present. Okay. We can conclude that, and with that we conclude the second problem of tutorial 3. Thank you.